Okay, I'm going to do another example. The region we have to rotate is defined by the following curves. The curve y equal to square root of x equal to 1, x equal to 2, y equal to minus 1. The axis of rotation is y equal to minus 1. So here's the diagram. Y-axis, x-axis, x equal to 1, x equal to 2, y equal to 1, y equal to 2, minus 1, and the curve y equal to y equal to square root x. This is the line y equal to minus 1. So that's the region that we have to rotate. And we have to rotate it around the axis y equal to minus 1. Okay, so this point goes here, this point goes about there. That's the three-dimensional volume we get by rotating the region around this line. Notice something. We're now rotating around an axis that's parallel to the x-axis rather than the y-axis, which is what we had in the previous example. But the procedure still stays the same. You pick a variable s that goes along the rotational axis. So here's s. For a fixed value of s, you find the point where the cross section perpendicular to that value of s, which is this. You find where it intersects the original region, and that point is here. So this variable, this is r, it's the radius of the disk. And now in the rotational coordinate system, the x coordinate of this point is s, the y coordinate of that point is r. So in the rotational coordinate system, this has coordinates sr. And let's draw the red rectangle corresponding to that coordinate system. In the original coordinate system, this point has coordinates x comma y, and the rectangle corresponding to that is this, because this is the original coordinate system. So this is x and this is y. And now we can write down the basic relations. So x is the same as s. So s equals x. Y goes from here to here, r goes from here to here. That distance is 1. So r equals y plus 1. And then finally the relation that relates x to y on this boundary, which is y equals square root of x. Now we have to find the limits of s. S is the same as x, and in the original region, x goes from 1 to 2, so the limits of s are also 1 and 2. So a is 1, b is 2, and the volume we are interested in is 1 to 2 pi r square ds. This formula is always the same. So pull the pi out, 1 to 2. We now have to figure out r in terms of s. So r equals y plus 1, which equals square root x plus 1, because y is square root x equals s. So this equals square root s plus 1, square root s plus 1 square ds. This is of course r square. Okay, now we just have to do this, and all right, I'll do this. So 1 to 2, we expand the square. Square root s squared is s plus 2 square root s plus 1 ds, which is of course very similar to the integral we did last time. So this is pi s square over 2 s raised to 3 over 2 pi 3 over 2 plus s. This is the integral of this term. This whole thing is the integral of this term. This is the integral of this term. And evaluate that between 1 and 2, and you're done. The point of this example is that the procedure is exactly the same, even if your axis of rotation ends up being parallel to the x-axis rather than parallel to the y-axis. Just make sure that the variable s that you choose is always along the axis of rotation. And when that's true, this formula always stays the same. And all you have to now do is figure out how r is a function of s from the basic relations.